Number 1, part A and part B. Find the GCD and LCM of 360 and 4000. In order to find the GCD and LCM, let's factor each number first. 360 can be factored as 20 times 18, use factor tree. 20 can be written as 4 times 5, and 4 can be factored as 2 times 2. 18 can be factored as 3 times 6, and 6 can be factored as 2 times 3. So factor 360 into primes. Then 360 can be rewritten as 2 to the power of 3, 3 to the power of 2, times number 5 to the power of 1. That's in the factor form of 360. Next, we factor 4000 into primes. 4000 can be factored as 4 times 1000. 4 can be factored as 2 times 2. 1000 can be factored as 10 times 10 times 10. 10 can be factored as 2 times 5, 2 times 5, another 2 times 5. So here we factor 4000 into primes. So 4000 can be written as 2 to the power of 1, 2, 3, 4, 5 times 5 to the power of 1, 2, 3. So first of all, factor both numbers into primes. For greatest common divisor, we first of all choose the common prime factor first. For 360 and 4000, the common prime factor is 2 and 5. Common prime factor is 2 and 5. And for each prime factor, choose the lowest power. For each prime factor, choose the lowest power. For number 2, the lowest power is power 3. And for number 5, the lowest power is power 1. Then multiply out. 2 to the power 3 times 5 is 40. Next, for the LCM, for the least common multiple, write down every prime factor. Write every prime factor exactly once. Write down every prime factor exactly once. We have 2, 3, and 5. Write every prime factor exactly once. Then choose the highest power. Then we choose the highest power. For number 2, the highest power is power 5. For number 3, the highest power is power 2. And for number 5, the highest power is power 3. Then multiply out. 2 to the power 5 times 3 squared times 5 to the power 3. Here I use my calculator, I get 36,000. Number 1, part C and part D. Try to find the GCD and LCM for these two numbers. When we have very large number, we try to use Euclidean algorithm for the GCD first. So for 1C, use Euclidean algorithm. GCD of 627, 205,143. When we see large numbers, we do long division. Take large number divided by small number. Here I use calculator. I get 327. 327 is the quotient. I take 327 times 627. I get 205,029. Then you subtract. Remainder is 114. Then by Euclidean algorithm, we replace larger number with the remainder. That equal to the GCD of 627 and 114. Next, apply Euclidean algorithm. You take larger number divided by smaller number. 627 divided by 114. 114 goes into 627 5 times. 5 times 114 is 570. Then subtract remainder is 57. Then we replace the larger number with the remainder. I get GCD of 57 and 114. Next, keep going. Take larger number, divide by smaller number. 114 divided by 57. 57 goes into 114 2 times. 2 times 57 is exactly 114, no remainder. So remainder is 0. Replace the larger number with the remainder. And GCD of 57 and 0 is 57. That's the greatest common divisor. Then for the least common multiple, there's a formula that says least common multiple of a, b, any two integer a, b, equal to the product of a, b divided by the greatest common divisor of a, b. So use this formula. LCM equal to 627 times 205,143 divided by the GCD. Use my calculator, I get 2,256,573. Number 2, part A. A equal to 315, B equal to 65. We try to write the GCD of A and B as a linear combination of A and B with integer coefficients. So first of all, let's find the GCD of AB using Euclidean algorithm. GCD of A and B. Use Euclidean algorithm. We first of all take larger number divided by smaller number. Take 315 divided by 65. 315 divided by 65. 65 goes into 315 4 times. 4 times 4 is 20. Carry 2 over. 4 times 6 is 24. 24 plus 2 is 26. 315 minus 26. We get 55. Then 315 divided by 65. 65 goes to 315 4 times. Remainder is 55. We write long division in this form. Then we replace the larger number with remainder. By Euclidean algorithm, replace the larger number with remainder. Then again, take larger number, divide by smaller number. Take 65, divide by 55. 55 goes into 65 1 time. Remainder is 10. We can also use long division to see it. 55 goes to 65 1 time. Remainder is 10. So I replace the larger number with the remainder. Then again, take larger number, divide by smaller number. Take 55, divide by 10. 10 goes into 55 5 times. Remainder is 5. So I can replace the larger number with the remainder. Then keep going, use larger number, divide by smaller number. Take 5, take 10, divide by 5. 5 goes to 10 2 times. Remainder is 0. So replace the larger number with the remainder. When one of the number becomes 0, the other number is the GCD. When one of the number turns to 0, the other number is the GCD of 315 and 65. So the GCD of these two numbers is 5. Next, we try to write 5 as a linear combination of 315 and 65 with integer coefficients. So in order to do that, let's try to get a remainder by itself. Ignore the large row. Ignore the large row. First of all, get remainder by itself. So the last row here, second last row here, I can write phi as 55 minus 5 times 10. For the second row, I can write 10 equal to 65 minus 1 times 55. For the first row, I can write 55 equal to 315 minus 4 times 65. Now, start from last row. We try to substitute. Start from last row. Phi equal to 55 minus 5 times 10. I replace 10 with the previous row. Replace 10 with the previous row. So 5 equal to 55 minus 5 times 65 minus 1 times 55. Replace 10 with the previous row. Then simplify here. Distribute 5, but don't multiply number out. I get 5 times 65. Distribute negative 5. Negative 5 times negative 1 is positive 5. So distribute negative 5 here. I get negative 5 times 65. Negative 5 times negative 1 is positive 5. So I get 5 times 55. Next, combine like terms. 55 plus 5 times 55 is 6 times 55. 55 plus 5 times 55 is 6 times 55. And 5 times 65 stays the same. So combine these two like terms. Next, replace the 55. Replace 55 with the first row. Next, replace 55 with the first row. 55 is 315 minus 4 times 65. Minus 5 times 65. Then distribute 6, but don't really multiply number out. Distribute 6, I get 6 times 315. Positive 6 times negative 4 is negative 24 times 65. Minus 5 times 65. Then I can combine like terms. Combine like terms. Negative 24, 65 and negative 5, 65. If I combine like terms, I get negative 9, 65. Leave everything else the same. So that's GCD of AB. Number 4 is GCD of AB equal to 6 times A. 6 times A minus 29 times B. This expression says GCD of AB equal to 6 times A minus 29 times B. Here I write GCD of AB as a linear combination of A and B with integer coefficients. This is the answer. Write GCD of AB as a linear combination of A and B. Number 2, part B. We try to write the GCD of these two numbers, AB, as a linear combination of AB with integer coefficients. We try to write the GCD of AB as a linear combination of these two numbers A and B with integer coefficients. So first step, we use Euclidean algorithm, find the GCD. So use Euclidean algorithm. I take the larger number divided by the smaller number. Take 247 divided by 121. 121 goes into 247 2 times. 2 times 141 is 242, so remainder is 5. Next, we take 121 divided by 5. Number 5 goes into 121 24 times. 5 times 24 is 120, so remainder is 1. Next, take 5 divided by 1. number 1 goes into 5 times, remainder is 0. So the GCD is 1. By Euclidean algorithm, the GCD of 247 and 121 equal to 1. Next, we try to write 1 as a linear combination of these two numbers, a and b, with integer coefficients. So we work backward. Start from the second last row. I can write 1 as 121 minus 24 times 5. First row, I can write 5 as 247 minus 2 times 121. Then substitute. Replace 5 with the first row. We have 1 equal to 121 minus 24 times 5. Replace 5 with the first row. I get 247 minus 2 times 121. Distribute 24. I get 121 minus 24 times 247 plus 48 times 121. 121 plus 48 times 121 is 49 times 121 minus 24 times 247. So I write the GCD of 247 and 121 as a linear combination of 247 and 121 with integer coefficients. Number 3, part A. 5x congruent to 6 mod 23. We try to solve the linear congruence for x. In order to solve for x, we try to find inverse of 5 mod 23. Find inverse of 5 first, then multiply both sides by inverse of 5. If I multiply both sides by inverse of 5, on the left side, number 5 inverse of 5 will be cancelled, we get x by itself. So let's find inverse of 5 first. In order to find inverse of 5 mod 23, we try to find some integer times 5 plus some integer times 23 that equal to 1. For small numbers, we can guess for the answer. Here, if I multiply 23 by 2, I get 46. If I multiply 5 by 9, I get 45. 46 minus 45 will be 1. So here, by guessing, I get negative 9 times 5 plus 2 times 23 equal to 1. So inverse of 5 congruent to negative 9. The number in front of 5 is the inverse of 5. So inverse of 5 congruent to negative 9 mod 23. The number in front of 5 is the inverse of 5. So inverse of 5 congruent to negative 9 mod 23. In general, try to make this number positive. So I can add 23. Negative 9 plus 23 is 14. Negative 9 plus 23 is 14. So inverse of 5 congruent to 14 mod 23. Then I multiply both sides by inverse of 5. Inverse of 5 congruent to 14 mod 23. If I multiply left side to the left side, right side to the right side, on the left side I get x by itself because number 5 inverse of 5 get cancelled. 6 times 14 is 84. Then if I take 84 divided by 23, take 84 divided by 23, remainder is 15. So x congruent to 15 mod 23, which means x equal to 15 plus 23t, where t can be any integer. That's the solution to this linear congruence. So for small numbers, we can guess the inverse of 5. But if we can guess, for example, if we can guess one number times 5 plus one number times 23 equal to 1, we can try to use Euclidean algorithm. If we can guess one number times 5 plus one number times 23 equal to 1, we can use Euclidean algorithm. So first of all, let's try to find GCD of 5 and 23 first. If I take 23 divided by 5, 5 goes into 23 4 times. Remainder is 3. So I replace the larger number with a remainder. Next, take larger number, divide by smaller number. 5 equal to, take 5 divided by 3. 3 goes into 5 one time. Remainder is 2. So I replace the larger number with a remainder. Next, take larger number, divide by smaller number. Take 3 divided by 2. 2 goes into 3 one time. Remainder is 1. Then replace the larger number with a remainder. Then take larger number, divide by remainder. Take larger number, divide by smaller number. 2 divided by 1. 1 goes into 2 2 times. Remainder is 0. Replace the larger number with a remainder. When one of the number becomes 0, the other number is the GCD of 5 and 23. Then I can try to write 1 as a linear combination of 5 and 23. So ignore the last row. For the other rows, get remainder by itself. So in the second last row, 1 equal to 3 minus 1 times 2. In the second row here, 2 equal to 5 minus 1 times 3. In the first row, 3 equal to 23 minus 4 times 5. Next, start from last row. Try to substitute everything. Start from last row. 1 equal to 3 minus 1 times 2. Replace 2 with the previous row. 2 is 5 minus 1 times 3. Then distribute 1. I get 1 times 5. Negative 1 times negative 1 is positive 1. 3 plus 1 times 3. If I combine like terms, 1, 3 plus another 1, 3 is 2 times 3. Minus 1 times 5. Next, I can replace 3 with the previous row. Replace 3 with the previous row. 3 equal to 23 minus 4 times 5. Replace 3 with the previous row. Then distribute 2. 1 equal to 2 times 23 minus a times 5 minus 1 times 5. Combine like terms. Negative a times 5 plus negative 1 times 5 is negative 9 times 5. So I write 1 equal to 2 times 23 minus 5, 9 times 5. If I try to match this form, we can see that negative 9 times 5 plus 2 times 23 equal to 1. The number in front of 5 is the inverse of 5. Then in general, try to make this number positive. So I can add 23 to this number. Inverse of 5 is 14. Inverse of 5 congruent to 14, not 23. So we get the same answer here. Substitute inverse of 5. Multiply both sides by inverse of 5. That's the solution to this linear congruence. Number 3, part B. We try to solve this linear congruence for x. So first of all, let's check what's the GCD between 17 and 99. If the GCD of 17 and 99 is 1, that means we're able to find the inverse of 17 mod 99. Then multiply both sides by inverse of 17. We can get s by itself. So first of all, let's check the GCD of 17 and 99 using Euclidean algorithm. Take 99 divided by 17. Seventeen goes to 99 5 times. 5 times 17 is 85. 99 minus 85 is 14. The remainder is 14. We replace the larger number with the remainder. Next, take 17 divided by 14. 14 goes to 17 one time. Remainder is 3. Replace the larger number with the remainder. Next, use larger number divided by smaller number. Take 14 divided by 3. 3 goes to 14 4 times. Remainder is 2. So replace the larger number with the remainder. Next, keep dividing. Take 3 divided by 2. 2 goes to 3 one time. Remainder is 1. Replace the larger number with the remainder. Next, take 2 divided by 1. 1 goes into 2 times. Remainder is 0. Replace the larger number with the remainder. So the GCD of 1 and 0 is 1. The GCD is 1. That means we're able to find the inverse of 17 mod 99. So to find the inverse, we need to first of all find some. We want to find some integer times 17 plus some integer times 99 equal to 1. In order to find integer coefficient for 17 and 99, again we use Euclidean algorithm. So let's work backward. Second last row, rewrite 1 as 3 minus 1 times 2. Next row, rewrite 2 as 14 minus 4 times 3. Next row, rewrite 3 as 17 minus 1 times 14. Next row, rewrite 14 as 99 minus 5 times 17. Now we try to substitute backward. Start from last row. 1 equal to 3 minus 1 times 2. Replace number 2 with the previous row. 1 equal to 3 minus 1 times 14 minus 4 times 3. Then distribute 1. I get negative 1 times 14 plus 4 times 3. Distribute negative 1. Then combine like terms. 1 3 plus 4 3 is 5 3. 1 equal to 5 times 3 minus 1 times 14. Next, replace 3 with the next row. 3 is 17 minus 1 times 14 minus 1 times 14. Then distribute 5. I get 1 equal to 5 times 17 minus 5 times 14 minus 1 times 14. Combine like terms. I get 5 times 17 minus 6 times 14. Then next, replace 14 with the previous row. Replace 14 with 99 minus 5 times 17. Then distribute 6. I get 6 times 99 plus 30 times 17. Then combine like terms. 5 times 13 plus 30 times 5 times 17 plus 30 times 17 is 35 times 17 minus 6 times 99. So the integer coefficient for 17 is 35. Integer coefficient for 99 is -6. That means inverse of 17 is 35. So inverse of 17 is 35 mod 99. Then I can multiply both sides by inverse of 17. 17x congruent to 4 mod 99. Inverse of 17 congruent to 35 mod 99. Multiply both sides. On the left side, 17 and inverse 17 get cancelled. We get s by itself. 4 times 35 is 140 mod 99. Then take 140 divided by 99, remainder is 41. That means x equal to 41 plus 99t for some integer t. Number 3, part C. X congruent to 4 mod 15. X congruent to 7 mod 8. X congruent to 3 mod 11. Solve the system of linear congruence for x. So here we can start from the largest modulus. Start from 15. S congruent to 4 mod 15. Start from the largest modular. S congruent to 4 mod 15 means s equal to 4 plus 15t, where t is an integer. Then I can substitute this x into the second largest modulus here. Substitute x here. For the second largest modular, x congruent to 3 mod 11. I can substitute. Replace x with 4 plus 15t. So 4 plus 15t congruent to 3 mod 11. Then for any number larger than 11, we take remainder. For any number larger than 11, take remainder. 15 divided by 11, remainder is 4. So 4 plus 4t congruent to 3 mod 11. Next, I can subtract 4 from both sides. Subtract both sides by 4. I get 4t congruent to -1 mod 11. In general, we try to make this number positive. So -1 plus 11 is 10. I have 4t congruent to 10 mod 11. Next, we try to find inverse of 4 mod 11. For small numbers, we can try to guess. Can we find an integer that times 4 plus an integer times 11 that equal to 1? For small numbers, we can try to guess. For larger numbers, use Euclidean Algorithm. So here we can guess 3 times 4 plus -1 times 11 equal to 1. The number in front of 4 is inverse of 4. So inverse of 4 congruent to 3 mod 11. So by guessing, we see that inverse of 4 congruent to 3 mod 11. Inverse of 4 congruent to 3 mod 11. Then I can multiply both sides by inverse of 4. On the left side, 4 and inverse of 4 get cancelled, we get t by itself. On the right side, 10 times 3 is 30. So t congruent to 30 mod 11. Then take 30 divided by 11. Since 30 is larger than 11, take 30 divided by 11, take remainder. 30 divided by 11, remainder is A. So T congruent to A by 11, which means T can be rewritten as A plus 11 times U, where U is an integer. Next, I can substitute T into this equation here to find X. So X equal to 4 plus 15T, where T is A plus 11U. Plug in T here. T is A plus 11U. Plug in here. I get 4 plus 11 times A plus 11U. Then simplify. If I distribute 15, 15 times A is 120. 15 times 11 is 165. Then combine like terms. 4 plus 120 is 124. S equal to 124 plus 165U. Next, I substitute X into the last linear congruence. Substitute X into the last linear congruence. I have 124 plus 165U congruent to 7 mod A. Substitute X into the last linear congruence. I got 124 plus 165U congruent to 7 mod A. Since 124 and 165 they are larger than A, take each number divided by A and take the remainder. 124 divided by A, remainder is 4. 165 divided by A, remainder is 5. Next, I can subtract 4 from both sides. I get 5U congruent to 3 mod A. Next, we try to get U by itself. So try to find inverse of 5. For small numbers, we can try to guess. Can we find some number times 5 plus some number times A that equal to 1? We know that 2 times A is 16. 3 times 5 is 15. So negative 3 times 5 is negative 15. Negative 15 plus 16 is 1. Since I make this equation equal to 1, inverse of 5 is a number in front of 5. So inverse of 5 congruent to negative 3 mod A. So inverse of 3 congruent, inverse of 5 congruent to negative 3 mod A. In general, we try to make this number positive. Since it's negative, I can add A here to make it positive. Negative 3 plus A is 5. So inverse of 5 congruent to 5 mod A. So inverse of 5 congruent to 5 mod A. Multiply both sides by inverse of 5. If I multiply both sides by inverse of 5, on the left side, 5 and inverse of 5 can cancel, you get U by itself. On the right side, 3 times 5 is 15. U congruent to 15 mod A. Since 15 is larger than A, take 15 divided by A, take remainder. 15 divided by A, remainder is 7. So U congruent to 7 mod A, which means U equal to 7 plus AV, where V is an integer. But we are looking for X. So I substitute U here. Substitute U here, we can find X. X equal to 124 plus 1. X equal to 124 plus 165 times U. U is 7 plus AV. Then simplify. If I distribute 165, I get 124 plus 1155 plus 1320V. Then when I combine like terms, I get 1279. plus 1320v, where v can be any integers. So that's the solution to the system of linear congruence. This is a solution to the system of linear congruence. Number 3, part D. X congruent to 7 mod 14. X congruent to 17 mod 20. X congruent to 12 mod 45. Solve the system of linear congruence for X. So we start from the linear congruence with the largest modular. Here, 44 is the largest modular. So we start from the last linear congruence. X congruent to 12 mod 45. That means S equal to 12 plus 45t, where t can be any integer. Next, we substitute x into the linear congruence that has the second largest modular, which is 20. 20 is the second largest modular. So x congruent to 17 mod 20. I replace x with 12 plus 45t. Since 45 is more than 20, I can take 45 divided by 20, take remainder. 45 divided by 20, take remainder, I get 5. Next, I can subtract both sides by 12. So 5t congruent to 5 mod 20. Next, we try to find inverse of 5 mod 20. But the GCD of 5 and 20 is not 1. We can't find the inverse of 5 mod 20. The GCD of 5 and 20 is not 1. So we can't find the inverse of 5 mod 20. What can we do here? Observe the middle number. If the GCD divides the middle number, then we can divide all three numbers by the GCD. Let's check. 5 divides 5. So here I can divide all three numbers by 5. Divide all three numbers by 5. 5 divided by 5t divided by 5 is 5. It's t. 5 divided by 5 is 1. So t congruent to 1 mod 20 divided by 5 is 4. So t congruent to 1 mod 4. That means t equal to 1 plus 4u, where u can be any integer. Then I can substitute t here, find x. X equal to 12 plus 45t, and t equal to 1 plus 4u. So x equal to 12 plus 45 plus 180u. Combine like terms, I get s equal to 57 plus 180u. Next, I substitute x into the last linear congruence. Substitute x into the last linear congruence. 57 plus 180u congruent to 7 mod 14. Substitute x into the last linear congruence. Now, since 57 and 180, they are both larger than 14, I take both numbers divided by 14 and take remainder. 57 divided by 14, remainder is 1. 180 divided by 14, remainder is 12. Then I can subtract 1 from both sides. 12u congruent to 6 mod 14. Next, try to find the inverse of 12 mod 14. But since, again, GCD of 14, GCD of 12 and 14 is not 1. We can't find the inverse. Here, GCD of 12 and 14 is not 1. We can't find the inverse. What should we do here? observe the middle number. If the GCD divides the middle number, we can divide all three numbers by the GCD. If the GCD doesn't divide the middle number, there's no solution. But since the GCD is 2, 2 divides 6, I can divide all three numbers by 2. Since 2 divides 6, I can divide all three numbers by 2. 12 divided by 2 is 6. 6 divided by 2 is 3. 14 divided by 2 is 7. Next, we can try to find inverse of 7, inverse of 6 plus 7. Next, we can try to find the inverse of 6 plus 7. For small numbers, we can guess for the answer. Can we find some number, some integer times 6 plus some integer times 7 equal to 1? We know that negative 1 times 6 plus positive 1 times 7 is 1. So the number in front of 6 is the inverse of 6. So inverse of 6 congruent to negative 1 plus 7. We try to make this number positive. So I can add 7. Inverse of 6 congruent to 6 plus 7. So inverse of 6 congruent to 6 plus 7. Multiply both sides by inverse of 6. On the left side, 6 and inverse of 6 get cancelled. We get u by itself. On the right side, 3 times u is 18. Since 18 is more than 7, I can take 18 divided by 7, remainder is 4. So u congruent to 4 plus 7, which means u can be written as 4 plus 7v, where v can be any integer. Then I can substitute u here, find x. I can substitute u here and find x. X equal to 57 plus 180 times 4 plus 7v. Distribute, I get 57 plus 720 plus 1260v. Combine like terms, I get 777 plus 1260v, where v can be any integers. That's the solution to the system of linear congruence. That's the solution to the system of linear congruence. Number 4, part A. 5x plus 17y equal to 20. Solve the linear differential equation for x and y. Here we can try to use linear congruence to solve this equation. This equation can be rewritten as 5 divides 17y minus 20. That can be rewritten as 17y congruent to 20 mod 5. Since 17 and 20 they are both larger than 5, we can take both numbers, divide by 5 and take the remainder. 17 divided by 5, remainder is 2. 20 divided by 5, remainder is 0. Next, we try to find inverse of 2 mod 5. For small number, we can guess. We try to find some integer times 2 plus some integer times 5 that equal to 1. We can guess 1 times 5 is 5. Negative 2 times 2 is negative 4. Negative 4 plus 5 is 1. Which means inverse of 2 congruent to negative 2. The number in front of 2 is the inverse of 2. Inverse of 2 congruent to negative 2 mod 5. In general, try to make this number positive. So I can add 5 to this number. If I add 5 to this number, inverse of 2 congruent to 3 mod 5. Inverse of 2 congruent to 3 mod 5. Multiply both sides by inverse of 2. On the left side, number 2 and inverse of 2 get cancelled, we get y by itself. On the right side, 0 times 3 is 0. So y congruent to 0 mod phi. That means y equal to phi t, where t can be any integer. Once I know y, I can plug in y, solve for x. Phi x plus 17, y is phi t, so I plug in. Phi x plus 17 times phi t equal to 20. I plug in phi t for y. Then solve an equation for x. Phi x equal to 20 minus 17 times phi t. If I divide both sides by phi, x equal to 4 minus 17t. So the solution to this linear differential equation is s equal to 4 minus 17t, y equal to 5t, where t can be any integers. That's the solution to this linear differential equation. Number 4, part B. Solve the linear differential equation. So first step, let's check if there is a solution. Let's find the GCD for 27 and 43 first. GCD of 27 and 43, there is 1. And 1 divides 50. So there is solution. If the GCD of 27 and 43 doesn't divide this number, there's no solution. So since 1 divides 50, there is a solution. So we try to use modulus to solve this differential equation. This equation can be rewritten as 27 divides 43y minus 50. That means 43y congruent to 50 mod 27. If I take 43 divided by 27, remainder is 16. If I take 50 divided by 27, remainder is 23. Next, we try to find inverse of 16 mod 27. We try to find inverse of 16 mod 27. That means we try to find some integer times 16 plus some integer times 27 equal to 1. The coefficient of 16 is the inverse of 16. So we can try to use Euclidean algorithm. 27 divided by 16. 16 goes into 27 one time. Remainder is 11. Then take 16 divided by 11. 11 goes into 16 one time. Remainder is 5. Then take 11 divided by 5. Number 5 goes into 11 two times. Remainder is 1. And 5 divided by 1. Number 1 goes into 5 times. Remainder is 0. So the GCD is 1. Let's work backward. Rewrite number 1 as 11 minus 2 times 5. Rewrite number 5 as 16 minus 1 times 11. Rewrite 11 as 27 minus 1 times 16. Then substitute backward. Number 1 equal to 11 minus 2 times 5. Replace number 5 with the previous row. I have 1 equal to 11 minus 2 times 16 minus 1 times 11. Distribute 2, I get 2 times 16 plus 2 times 11. 11 plus 2 times 11 is 3 times 11. Minus 2 times 16. Then replace 11 with the first row. 1 equal to 3 times 27 minus 1 times 16 minus 2 times 16. 3 times 27, take 3 times negative 1, I get negative 3 times 16 minus 2 times 16. Combine like terms. 1 equal to 3 times 27 minus 5 times 16. So we know that negative 5 times 16 plus 3 times 27 equal to 1. That means inverse of 16 is negative 5. So inverse of 16 congruent to negative 5 mod 27. If we try to make it positive, I can add 27 to both sides. Inverse of 16 congruent to 22 mod 27. Since we know that 16y congruent to 23 mod 27, I can multiply left side to the left side, right side to the right side. So y congruent to 506 mod 27. Then take 506 divided by 27. Take 506 divided by 27, take a remainder. I get 20. That means y equal to 20 plus 27t. That means y equal to 20 plus 27t. Then once I know y, I can substitute y, solve for x. So we have 27x plus 43 times y equal to 50. Solve the equation for x. 27x plus 860 plus 43 times 27t, I don't know what it is, let's leave it for now, equal to 50. Then I try to solve the equation for x. I can subtract both sides by 860 and move this term over. I have 27x equal to negative 810 minus 43 times 27t. In order to get s by itself, I divide both sides by 27. S equal to negative 30 minus 43t. So the solution is s equal to negative 30 minus 43t, y equal to 20 plus 27t, where t can be any integers. Number 4, part C. 9x plus 15y plus 40z equal to 49. Solve this linear differential equation. First of all, let's check the GCD of the coefficients. GCD of 9, 15, and 40 is 1. 1 divides 49. So this equation has solutions. If the GCD doesn't divide 49, then there's no solution. There's no integer solutions. So let's solve two of the variables first. Set 9x plus 15y equal to 3w. Because the GCD of 9 and 15 is 3. In order to guarantee this equation has a solution, 9x plus 15y must be a multiple of 3. So I let 9x plus 15y equal to 3w. Then this equation can be rewritten as 3w plus 40z equal to 49. Next, we try to solve the equation using linear congruence. So this equation can be rewritten as 3 divides 40z minus 49. That can be rewritten as 40z congruent to 49 plus 3. Since 40 and 49 they are both larger than 3, take each number, divide by 3, take remainder. 40 divided by 3, remainder is 1. 49 divided by 3, remainder is also 1. So z equal to 1, z congruent to 1 plus z congruent to 1 minus 3. So z can be rewritten as 1 plus 3t, where t can be any integer. Once I know z, I can substitute here, solve for w. I get 3w plus 40z, z is 1 plus 3t, equal to 49. Then solve an equation for w. 3w plus 40 plus 120t equal to 49. So 3w can be rewritten as 9 minus 120t. 3w equal to 9 minus 120t. Divide both sides by 3. W equal to 3 minus 40t. Next, we try to solve for x and y based on w. Try to solve for x and y. We have 9x plus 15y equal to 3w. Since the GCD of 9 and 15 is 3, and 3w is a multiple of 3, I can divide both sides by 3. This equation can be rewritten as 3x plus 5y equal to w. Then solve this equation using linear congruence. This equation can be rewritten as 3 divides 5y minus w. That means 5y congruent to w minus 3. And we know that w is 3 minus 40t. So 5y congruent to 3 minus 40t minus 3. Since 5 is more than 3, I can take 5 divided by 3, take remainder. 5 divided by 3, remainder is 2. 3 divided by 3, remainder is 0. 40 divided by 3, remainder is 1. So 2y congruent to negative 1t minus 3. If we try to make the coefficient positive here, I can add 2. Negative 1 plus 2 is 2. So 2y congruent to 2t minus 3. Next, we can try to find the inverse of 2 minus 3. Next, we can try to find the inverse of 2 minus 3. Then multiply both sides for linear congruence by inverse of 2. We try to find some integer times 2 plus some integer times 3 equal to 1. For small numbers, we can guess an answer. We know that 2 times 2 plus negative 1 times 3 is 1. So the coefficient of 2, the number in front of 2, is the inverse of 2. The number in front of 2 is the inverse of 2. So inverse of 2 is 2 minus 3. The number in front of 2 is the inverse of 2. So inverse of 2 congruent to 2 minus 3. So multiply both sides by inverse of 2. On the left side, 2 and inverse of 2 can cancel, we get y by itself. On the right side, 2 times 2t is 4t. 4 is more than 3, so I take 4 divided by 3, remainder is 1. So y congruent to 1t minus 3. 1t is the same as t. So y congruent to t minus 3. That means y equal to t plus 3 times s, where s can be any integer. Then I plug in y. I can solve an equation for x. I have 3x plus 5y, y is t plus 3s, equal to w. W is 3 minus 40t. Then solve an equation for x. 3x plus 5t plus 15s equal to 3 minus 40t. That means 3x equal to 3 minus 45t minus 15s. If I divide both sides by 3, s equal to 1 minus 15t minus 5s. So the answer is s equal to 1 minus 15t minus 5s, y equal to t plus 3s. Z equal to 1 plus 3t, where s and t can be any integers. That's the solution to these linear differential equations. Number 4, part D. Solve this linear differential equation. First of all, let's check, see if it has a solution or not. Let's first of all find the GCD for 12, 20, and 39. GCD of 12 and 20 is 4, and GCD of 4 and 39 is 1. Since 1 divides 91, it has solution. So since it has solution, let's solve two of them first. For 12x plus 20y, I set equal to 4w. Since the GCD of 12 and 20 is 4, to guarantee this equation has a solution, I need to set equal to 4w. To guarantee this equation has a solution, I must set equal to 4w, because GCD of 12 and 20 is 4. So this equation can be rewritten as 4w plus 39z equal to 91. Next, I use linear congruence to solve this equation here. I use linear congruence to solve this differential equation. I can write it as 4, I can rewrite this equation as 4 divides 39z minus 91. That means 39z congruence to 91 mod 4. (39) divided by 4, remainder is 3. 91 divided by 4, remainder is also 3. Next, we try to find inverse of 3 mod 4. Next, we try to find inverse of 3 mod 4. We try to find something times 3 plus something times 4 equal to 1. That's easy. We can try the number. We don't need to use Euclidean algorithm. We can try this number out. We know negative 1 times 3 plus 1 times 4 is 1. That means inverse of 3 congruent to negative 1 mod 4. In order to make this number positive, I can add 4 to negative 1. Negative 1 plus 4 equal to 3. So inverse of 3 congruent to 3 mod 4. Inverse of 3 congruent to 3 mod 4. So inverse of 3 congruent to 3 mod 4. I multiply both sides by inverse of 3. On the left side, I get z by itself. On the right side, 3 plus 3 is 6. So 3 times 3 is 9. Number 9 divided by 4, remainder is 1. So z equal to 1 plus 4t, where t is an integer. Next, substitute z into this equation, we can solve for w. Substitute z into this equation, I can solve for w. I have 4w plus 39 times 1 plus 4t equal to 91. Distribute 39, I get 4w plus 39 plus 156t equal to 91. Then solve the equation for w. 4w equal to 52 minus 156t. Then I can divide both sides by 4. W equal to 13 minus 39t. Now here I know the solution for z and w. Now I know the solution for z and w. Next, I can solve this equation for x and y. Next, I can solve this equation for x and y. We know that 12x plus 20y equal to 4w. Since the GCD of 12 and 20 is 4, I can divide every term by 4. I guess 3x plus 5y equal to w. Let's solve this differential equation using linear congruence. It can be rewritten as 3 divides 5y minus w. That means 5y congruent to w plus 3. We know w is 13 minus 39t. Substitute here. 5y congruent to 13 minus 39t plus 3. Divide every number by 3, take remainder. 5 divided by 3, remainder is 2. 13 divided by 3, remainder is 1. 39 divided by 3, remainder is 0. So 2y congruent to 1 plus 3. Next, we try to find the inverse of 2 plus 3. Inverse of 2 plus 3. That means we try to find some integer times 2 plus some integer times 3 equal to 1. If the number is small, we can try it out. When the number is large, we use Euclidean algorithm. When the numbers are small, you can try the answer. We know negative 1 times 2 plus 1 times 3 is 1. That means inverse of 2 congruent to negative 1 plus 3. In order to make a positive number here, add 3 to this number. So inverse of 2 congruent to 2 plus 3. Inverse of 2 congruent to 2 plus 3. Substitute here. Inverse of 2 congruent to 2 plus 3. And multiply both sides. I get y congruent to 2 plus 3. That means y equal to 2 plus 3 times s, where s is an integer. You can use any letter for integer, but don't use the same one. We use letter t already. Don't use the same one. Use a different letter for s. So y equal to 2 plus 3s. Then, since I know y, I know w, I can substitute to find x. Since I know y, I know w, I can substitute to find x. So I have 3x plus 5y, y is 2 plus 3s, equal to w. W is 13 minus 39t. Then solve this equation for x. Distribute 5, I get 10 plus 15s equal to 39, equal to 13 minus 39t. Next, we'll try to solve an equation for x. So I can subtract 10, I get 3 here. Subtract 10, subtract 15s. I get 39t minus 15s. Then divide both sides by 3. X equal to 1 minus 13t minus 5s. So the solution is x equal to 1 minus 13t minus 5s. Y equal to 2 plus 3s. Z equal to 1 plus 4t, where s and t are integers. Where s and t could be any integers. Number 5, part A. F is a function from real number to real number, and f is defined as f of x equal to 9 minus s squared. We try to find the image and inverse image of function f. First one, the image of the set -1, 2. The image of the set -1, 2. If I substitute -1, I get A. If I substitute 2, I get 5. So the set of A, 5 is the same as the set 5, A. Usually put the element in order. That's a little easier. Next, the image of the set, the image of the interval from -1 to 2. The image of the interval from -1 to 2. For interval, I suggest we use a graph. For interval, I suggest to use a graph. If we sketch a graph for f of x, it's an upside down parabola. Y-intercept is 9. S-intercept is -3 and +3. So -1 to 2 somewhere here. The image of -1 to 2 represent this piece of curve. When s is between -1 and 2, we have this piece of graph. Then we try to find the corresponding y coordinate. When s is -1, y is A. When s is 2, y is 5. If I find a projection in the y-axis, that means I push everything into y-axis. If I find a projection in the y-axis, this is an open interval. Number 4 is not included. Projection in y-axis is everything from 5 to 9. That's the projection in the y-axis. It's everything from 5 to 9. Not including 5, but including 9. Not include 5, but include 9. So that's the interval from 5 to 9, not including 5, but including 9. Next, the image of the closed interval from 1 to 2. Image of the closed interval from 1 to 2. Again, we use the graph. For intervals, we use graph. It's an upside down parabola. From 1 to 2. When s is 1, the image is A. Since 1 is not included, A is not included. Image of 2 is 5. In the curve, it represents this piece. F of 2 is 5. Since 1 and 2 they are included, so the endpoint will be included. So it's an interval from 5 to A. Since the endpoint here is included, 5 and A will both be included. So that's the interval from phi to a, include both endpoints. Next, the image from 2 to infinity, image of the set from 2 to infinity. Again, for intervals, use graph. From 2 to infinity. When s is 2, y is 5. Since 2 is included, 5 will be included. Then for x from 2 to infinity, it represents this piece in the graph. For s from 2 to infinity, it represents this piece in the graph. Then we find the projection in the y-axis. We find everything here below phi. So the projection in y-axis is from phi to negative infinity. So that's the interval from negative infinity to 5, including 5. Next, f of the image of the interval from negative infinity to 2. Image of the interval from negative infinity to 2. Again, we use graph. Two is here. Its y coordinate at 2 is 5. Since 2 is not included, 5 is not included. Then we are looking for the interval from negative infinity to 2. From negative infinity to 2, it represents this piece of graph. From negative infinity to 2, it represents this piece of graph. Then to find the image of the interval, we find the projection in the y-axis. In the y-axis, if I push the graph to the y-axis, I have everything below 9. I have everything below 9, including 9. So that's the interval from negative infinity to 9, including 9. That's the image of the graph. That's the image of the interval. Next, find the inverse image. Inverse image of the interval of the set 5, A, 9. Image of interval is the set of inverse image of interval is the set of all x. The set of all x in the domain. The set of all x in the domain such that f of x equal to 5, A, or 9. That means the set of all x in the domain such that 9 minus s squared equal to 5 equal to A equal to 9 or equal to 9. If I set 9 minus s squared equal to 5, solve an equation, I get positive negative 2. If I set 9 minus s squared equal to A, solve an equation, I get s equal to positive negative 1. If I set this equation equal to 9, solve an equation, I get s equal to 0. Then put the numbers in order. I have negative 2, negative 1, 0, 1, 2. Next, find the inverse image. Find the inverse image of the interval from 5 to A. For intervals, for image or inverse image of an interval, we use graph. Let's use graph. from 5 to a. Y-intercept is 9. 5 to a is somewhere here. Not including 5, not including a. Interval from 5 to a represents this piece in the y-axis. The corresponding graph is this piece and this piece. When y is 5 to a, that's the corresponding graph. Then we can find the s coordinate. When y is 5, s is negative 2 and 2. When y is 8, x is negative 1 and 1. Since y is between 5 and 8, x is between negative 2 and negative 1 and positive 2 and positive 1 and positive 2. So we have two pieces. Interval from negative 2 to negative 1, union the interval from negative 1, from positive 1 to 2. Next, the inverse image of an interval from 9 to 16. Inverse image of an interval from 9 to 16. Again, try to use the graph. From 9 to 16. 9 to 16 is somewhere here. 9 to 16. And for this piece, there's no image. There's no inverse image because the range of the graph is from negative infinity to 9. From 9 to 16, there's no inverse image. 9 to 16 is here. There's no inverse image above 9. There's no inverse image above 9. So the inverse image is NP set. Next one. Find the inverse image of the closed interval from 9 to 16. Since the range is from negative infinity to 9, so only number 9 has inverse image. Only number 9 has inverse image. From 9 to 16. 9 to 16 is somewhere here. From 9 to 16. Only number 9 has an inverse image 0. Only number 9 has inverse image 0. Everything above 9 doesn't have inverse image. So that's the same as inverse image of number 9. Only number 9 has an inverse image. And the inverse image of number 9 is 0. It's the set of 0. The image and inverse image is a set. So inverse image of number 9 is the set of 0. Next. Inverse image of the interval from negative infinity to 0. Inverse image of the interval from negative infinity to 0. Let's draw the graph. Inverse image from negative infinity to 0. Not including 0. So the corresponding piece in the graph is this tail and this tail. For these two tails, when y is 0, x is negative 3 and positive 3. So the inverse image in the x-axis is from negative 3 to negative infinity and from 3 to infinity. That's the inverse image of the interval from negative infinity to 0. It's from negative infinity to negative 3 and from 3 to infinity. Number 5, part B. F is a function from real number to real number, and f of x is the floor function of half of x plus 1. Find each of the following sets. First one, the image of the set of 9 over 4. This set contains only one element, so we plug in 9 over 4 into the function. F of 9 over 4 is the floor function of half times 9 over 4 plus 1. Half times 9 over 4 is 9 over 8. 9 over 8 plus 1 is 2 and 1 over 8. If I take floor function, it's 2. So the image of the set 9 over 4 is the set of 2. Next, the image of the interval from half to 10 over 3. Image of the interval from half to 10 over 3. In this interval, we know that x is between half and 10 over 3. The function half of x plus 1 is an increasing function. So half of x plus 1 is between half times half plus 1 and half times 10 over 3 plus 1. Since this is an increasing function, s is between half and 10 over 3. So half of x plus 1, the function, half of x plus 1 is between half times half plus 1 and half times 10 over 3 plus 1. Then simplify. The left side here, half times half is a quarter. Quarter plus 1 is 1 and a quarter. Half times 10 over 3 is 5 over 3. 5 over 3 plus 1 is 2 and 2/3. Next, let's use a number line to find the image. 0, 1, 2, 3. 1 and a quarter somewhere here. 2 and 2/3 somewhere here. So half of x plus 1 is somewhere between 1 and a quarter and 2 and 2/3. For a number from 1 and a quarter and to 2, if I take floor function, the image is 1. For number between 2 and 2 and 2/3, if I take floor function, the image is 2. So the image of this interval is 1 and 2. It's the set of 1 and 2. For values between 1 and a quarter and 2, the image is 1, if I take floor function. And for the values between 2 and 2 and 2/3, if I take floor function, the image is 2. That's why the image of this interval is 1 and 2. Next, the image of the set 1 and 6. This set contains only 2 elements, so we find image for each element individually. For f of 1, we plug in 1 into the function. I get floor of half times 1 plus 1. Half times 1 plus 1 is 1 and a half. If I take floor function, it becomes 1. For f of 6, I have half times 6 plus 1. Half times 6 is 3. 3 plus 1 is 4. Floor function of 4 is 4. So the image of the set 1, 6 is the set 1, 4. Next, the image of the interval from 1 to 6. We know that in this interval, from 1 to 6, x is between 1 and 6. Half of x plus 1 is an increasing function. So half of x plus 1 is between half times 1 plus 1 and half times 6 plus 1. Half times 1 plus 1 is 1.5. Half times 6 plus 1 is 4. Next, we use number line to find the image. 0, 1, 2, 3, 4, 5. 1.5 is here. 4 is here. Half of x plus 1 is between 1.5 and 4. Not including 4. So for the numbers between half and 2, the image is 1. For the numbers between 2 and 3, if I take floor function, image is 2. For the number between 3 and 4, if I take floor function, the image is 3. So the image is 1, 2, and 3. For numbers between half and 2, 1.5 and 2, if I take floor function, the image is 1. For numbers between 2 and 3, if I take floor function, the image is 2. For numbers between 3 and 4, if I take floor function, the image is 3. So the image is 1, 2, and 3. Next, the image of the closed interval from 1 to 6. Same thing. X is between 1 and 6, but now since it's closed interval, 1 and 6 now are included. So half of x plus 1 is between half times 1 plus 1 and half times 6 plus 1, including the endpoint. Here, half of x plus 1 is between 1.5 and 4, including 1.5 and 4. Then use number line to find the image. Half is here. Now endpoint here is included. 4 is here. Half of x plus 1 is between half, 1.5 and 4. Endpoints are included. Next, let's find the image. For numbers between half, 1.5 and 2, if I take floor function, the image is 1. For numbers between 2 and 3, if I take floor function, the image is 2. For numbers between 3 and 4, if I take floor function, the image is 3. And for number 4 itself, if I take floor function, it stays at 4. So the image is 1, 2, 3, 4. Because if I take floor function for number 4, it stays at 4. So the image of this interval is from 1, 2, 3 to 4. Next, we are looking for the inverse image of the set 1 and 2. For inverse image, we try to find out for which x its image is 1 or 2. So here we can try to use a number line. This function contains a floor function here. We know that for numbers between 1 and 2, its image is 1. And for numbers between 2 and 3, not including 3, its image is 2. So if the image is from 1 to 2, half of x plus 1 must be between 1 and 3, including 1 and not including 3. Then we can solve this inequality for x. I can subtract 1 from all 3 parts. Half of x is between 0 and 2. Then multiply all 3 parts by 2. S is between 0 and 4, including 0 but not including 4. So the inverse image of the set 1, 2 is the interval from 0 to 4, including 0 but not 4. Next, find the inverse image of the interval from 1 and 2. This function contains floor function. We know that the image of floor function is always whole number. So that means only whole number has inverse image. For the interval from 1 to 2, there's no whole numbers between 1 and 2. That means there's no inverse image. For numbers between 1 and 2, there's no whole numbers, so there's no inverse image. Only whole number has inverse image. For the interval from 1 to 2, there's no whole numbers, so that's why there's no inverse image. Next, inverse image of the closed interval from 1 to 2. We know that only whole number has inverse image. For the closed interval from 1 to 2, the only whole number in the set is the set 1 and 2. Those are the only whole number in the set. And from the previous parts, we know that the inverse image of the set 1, 2 is the interval from 0 to 4, including 0 but not 4. Next, inverse image of the set 2.2 and 3.7. Since only whole number has inverse image, since for floor function only whole number has inverse image, in this set there's no whole number, so there's no inverse image. Since only whole number has inverse image, and in this set there's no whole numbers, so there's no inverse image. Next, we're looking for the inverse image of the interval from 2.2 to 3.7. We know that for floor function, only whole number has the inverse image. In the interval from 2.2 to 3.7, the only whole number is number 3. So the inverse image of this interval is the same as the inverse image of the set of number 3. In order to find the inverse image of number 3, we try to use number line. We try to find out for which x its image is number 3. We know that for floor function, for all numbers between 3 and 4, its image is number 3. So for the inverse image of number 3, for inverse image of number 3, half of x plus 1 must be between 3 and 4, including 3 but not 4. Then we can try to solve this inequality for x. Subtract 1 from all 3 parts. Half of x is between 2 and 3, including 2 but not including 3. Then we can multiply all 3 parts by 2. S is between 4 and 6, including 4 but not 6. So the inverse image of number 3 is the interval from 4 to 6, including 4 but not 6. Number 6, part A. F is a function from real number to real number, and f of x is 4x cubed minus 1. We try to determine whether f is 1 to 1. If f assigns every element in the domain to different elements in the codomain, then f is 1 to 1. But if f assigns 2 different elements in the domain to the same element in the codomain, then f is not 1 to 1. Here, f of x is 4x cubed minus 1. Let's test a few numbers. If I plug in 0, I get negative 1. If I plug in 1, I get 3. If I plug in 2, I get 31. It looks like function f assigns different elements in the domain to different elements in the codomain. So it looks like f is 1 to 1. Let's try to prove it. So to prove f is 1 to 1, we use this definition here. For all s1, s2 in A, if f of s1 equal to f of s2, then s1 equal to s2. So let x1, s2 belongs to the domain. Here the domain is R, the set of all real numbers. Let x1, s2 belong to the domain. Assume f of s1 equal to f of s2. Then, if I substitute x1 for x, I get 4s1 cubed minus 1. If I substitute x2 for x, I get 4x2 cubed minus 1. We try to show that x1 equal to x2. So here I can add 1 to both sides. If I add 1 to both sides, I have 4s cubed, 4s1 cubed equal to 4s2 cubed. Then I can divide both sides by 4. I get s1 cubed equal to s2 cubed. Then I can take cube root on both sides. Taking the cube root on both sides, I make s1 equal to s2. Since f of s1 equal to f of s2 implies s1 equal to s2, then I can say f is 1 to 1 function. Then f is 1 to 1. Part C. F is a function from real number to real number. F of x equal to s cubed minus s squared plus 2. If f assign every element in the domain to different elements in the codomain, then f is 1 to 1. But if f assign two different values in the domain to the same value in the codomain, then f is not 1 to 1. Let's test a few values here. If I plug in 0, I get 2. If I plug in 1, I also get 2. Since f assigns two different values in the domain to the same value in the codomain, f is not 1 to 1. So here, use a definition to prove f is not 1 to 1. So let x1 equal to 0, x2 equal to 1 in the domain. Here, 0 and 1, they are both real numbers, so they both belong to the domain. Then x1, s2 belong to the domain. F of s1 equal to f of 0, which is 0 cubed minus 0 squared plus 2 equal to 2. F of s2 is f of 1, which is 1 cubed minus 1 squared plus 2 equal to 2. Since f of s1 equal to f of s2, but s1 doesn't equal to s2, then f is not 1 to 1. Number 6, part B. F is a function from real number to real number, and f of x is square root of s squared plus 1. Determine whether f is 1 to 1. If function f assign every element in the domain to a different element in the codomain, then f is 1 to 1. But if f assign two different elements in the domain to the same element in the codomain, then f is not 1 to 1. Observe this function. Is this function 1 to 1? We have x squared here. For x squared, if I plug in positive 1 and negative 1, I get exactly the same value. So that means f assign positive 1 and negative 1 to the same element in the codomain. This f is not 1 to 1. To show it's not 1 to 1, we need to give an example that show that there's s1, s2 in the domain such that f of s1 equal to f of s2, but s1 doesn't equal to s2. So to prove f is not 1 to 1, give an example, give a counter example. Let's call counter example. So let s1 equal to negative 1 and x2 equal to positive 1 belong to the domain. F of s1 equal to f of negative 1, which is square root of negative 1 squared plus 1 is square root of 2. f of x2 is f of 1. That equal to square root of 1 squared plus 1. That's also square root of 2. Since f of s1 equal to f of s2, but s1 doesn't equal to s2, then f is not 1 to 1. Part D. Let f be a function from integer to integer, and f of x is floor function of x plus ceiling function of x. Is this function 1 to 1? If f assign every element in the domain to a different element in the codomain, then f is 1 to 1. Let's try some values. If I substitute 0, floor function of 0 is 0, ceiling function of 0 is 0, 0 plus 0 is 0, I get 0. F of 0 is 0. If I substitute 1, f of 1 is floor function of 1 plus ceiling function of 1. Floor function of a whole number is the whole number itself. Ceiling function of a whole number is the whole number itself. So 1 plus 1 is 2. F of 2, if I substitute 2, floor function of 2 is 2. Ceiling function of 2 is 2. 2 plus 2 is 4. So it looks like f assign every element in the domain to a distinct element in the codomain. So it looks like f is 1 to 1. It looks like f is 1 to 1. So let's prove it. To prove f is 1 to 1, we need to use this definition. For all s1, s1, s2 in the domain, if f of s1 equal to f of s2, then s1 must equal to s2. So let's prove it. Let's prove it. Let s1, s2 belong to the domain. Sorry, domain is C. Domain is here. Let s1, s2 belong to the domain. Then they are whole numbers. Assume f of s1 equal to f of s2. Assume f of s1 equal to f of s2. Then I have floor function of s1 plus ceiling function of s1 equal to floor function of s2 plus ceiling function of s2. Since s1, s2 they are integers, floor function of integers stays the same. Ceiling function of integers stays the same. Floor function of integers stays the same. Ceiling function of integers stays the same. That's s1. s1 plus s1 is 2s1. s2 plus s2 is 2s2. Then I can divide both sides by 2. s1 equal to s2. We assume f of s1 equal to f of s2, and we prove that s1 equal to s2. So f is 1 to 1. Number 7, part A. F is a function from real number to real number, and f of x equal to 1 over x squared plus 1. We try to determine whether f is onto or not. For any function f, if its codomain and range are exactly the same, then f is onto. Otherwise, f is not onto. For this function f from real number to real number, its codomain is the set of all real number. That's the codomain. How about the range? Are they the same? Range represents the set of all possible outcomes that f can have. F of x is 1 over x squared plus 1. 1 over any number can never be 0. 1 over any number can never be 0. So 0 doesn't belong to the range, but 0 belongs to the codomain. So here, range and codomain are not the same. This function f is not onto. So in order to show the function is not onto, use a definition. There's a y in B such that for all x in A, f of x not equal to y. So let 0 belong to B. Let 0 belong to the codomain. Then for all x in the domain, x squared is always greater or equal to 0. So x squared plus 1 is always strictly greater than 0. So the reciprocal 1 over x squared plus 1 is also greater than 0. So f of x equal to 1 over x squared is always strictly greater than 0. Hence, f of x doesn't equal to y. Something greater than 0 cannot be 0. Something greater than 0 cannot be 0. So f is not on 2. Part C. F is a function from the set of all real numbers to the set of all integers. F of x equal to the floor function of x over 2. If the range and the codomain is exactly the same, then function f is on 2, otherwise it's not on 2. Here the codomain is the set of all integers. How about the range? Let's take a look at the range. If I plug in 0 to the function, I get 0. If I plug in 1, floor function of half is also 0. If I plug in 2, I get 1. If I plug in 3, I also get 1. If I plug in 4, I get 2. So it looks like I'm able to get all integers here. It looks like we're able to get all integers here. So we may think of that the range is the same as the codomain. So function f is on 2. So in order to prove function f is on 2, use definition, which says for all y in the codomain, there's x in the domain such that f of x equal to y. So here the domain is the set of all real number, the codomain is the set of all integers. Let y belong to, is the definition, let y belong to the codomain. We try to find x in the domain such that f of x equal to y. So let x equal to 2y. 2 times the integer is a real number, so 2y. X belongs to the domain. Then f of x equal to f of 2y. Here, x equal to 2y. So f of x equal to f of 2y. For f of 2y, I plug in 2y into the function f. I get the floor function of 2y over 2. We know that 2y over 2 is the same as y. So we get floor function of y. Since y is an integer, floor function of integer is the same as the integer itself. Floor function of integer is the same as the integer itself. So f of s equal to y. Since for all y in the codomain, there's x in the domain such that f of s equal to y. So f is on 2. Number 7, part B. F is a function from integer to integer, and f of x is defined as 3x plus 4. We try to determine whether f is on 2 or not. If a function is on 2, then its range must be the same as the codomain. The codomain here is the set of all integers. What's the range? Let's plug in some number from domain to see what's the range. Domain contains all integers. If I plug in 0, what do I get? F of 0 is 0. F of 0 is 4. F of 1 is 7. F of 2 is 10. F of negative 1 is 1. F of negative 2 is negative 2. it looks like we skip a lot of numbers between 1 and 4, between 4 and 7, between 7 and 10. So this function can never reach 0. This function can never reach 0. F of s can never equal to 0. So it won't be on 2. It won't be on 2. This function can never reach 0. 0 is in the codomain, but it's not in the range. It's not in the range. So f is not on 2. So let's prove it. Let's try to prove f is not on 2. To show f is not on 2, we try to show that there is y in B, such that for all x in A, f of x doesn't equal to y. So let's try to show that f is not on 2. So we know that 0, let 0 be an element in the codomain. Let y equal to 0 in the codomain. The codomain is all the set of all integers. We try to show f of x not equal to y. We try to prove by contradiction. Assume there is x. Assume there is x in the domain such that f of x equal to y. Then 3x plus 4 equal to 0. That means s equal to 4 over 3, which is not in the domain, which is not integer. So that's a contradiction. X is in the domain. We prove that s is not in the domain. That's a contradiction. So it's a contradiction. So it doesn't exist x. It doesn't exist x in the domain. That means for all x in the domain, f of x doesn't equal to y. So for all x in the domain, f of x doesn't equal to y. So f is not on 2. Part D. Let f be a function from real number to the interval, to the closed interval from -1 to 1. Let f of x defined as sin x. Is f an on-to function? For sine function from real number to interval, let's try to draw the graph, see how it looks like. Sine function from -1 from all real number to the interval, closed interval from -1 to 1. Sine function looks like this. Its lower bound is -1, upper bound is +1. So it looks like this function is on 2. If I find a projection in the y-axis, I get an interval from -1 to 1. It looks like this function is on 2. So to show it's on 2, we need to show that for all y in the codomain, there's x in the domain such that f of x equal to y. So let's pick random element in the codomain. So let y belong to the codomain. Let y belong to the codomain. We try to find some x in the domain such that f of x equal to y. Let x equal to inverse sine of y. Then f of x equal to f of inverse sine of y equal to f inverse equal to sine of inverse sine of y. I plug in inverse sine for x, and sine of inverse sine actually is y. So f is on 2. Number A, part A. Let A and B be positive integers. Show that if A divides B, then A is less than or equal to B. So let's prove it. A divides B. By definition, it means A times some integer k equal to B, where k is an integer. A divides B means A times k equal to B for some integer k. So which means k can be rewritten as B over A. If I divide both sides by A, k can be rewritten as B over A. Since both A and B are positive, then k must be positive. Since both A and B are positive, then k must be positive, because positive number over positive number is positive. Since k is positive, then positive integer must be greater or equal to 1. K is an integer, and k is positive, so k must be greater than or equal to 1. If I multiply both sides by k, if I multiply both sides by A, so AK is greater or equal to A. If I multiply both sides by A, I have AK is greater or equal to A. Since A is positive, I multiply both sides by letter A. Inequality stays the same. Inequality sign stays the same. So B is greater or equal to A. A times K is B. So B is greater or equal to A. That's the proof. Number 8, part B. Let A and B be integers. Show that if 3 doesn't divide A and 3 doesn't divide B, then 3 doesn't divide A squared plus B squared. Let's prove it. If 3 doesn't divide A, that means either A congruent to 1 plus 3 or A congruent to 2 plus 3. If 3 doesn't divide A, that means when you take A divided by 3, there's a remainder. Remainder is either 1 or 2. So A congruent to 1 plus 3, that means A squared congruent to 1 plus 3. A congruent to 2 plus 3 means A squared congruent to 4 plus 3. A squared congruent to 4 plus 3. If I take 4 divided by 3, remainder is 1. So A squared also congruent to 1 plus 3. So in both cases, A squared congruent to 1 plus 3. So in both cases, A squared congruent to 1 plus 3. Similarly, three doesn't divide B. That means B squared congruent to 1 plus 3. Similarly, since 3 doesn't divide B, B squared congruent to 1 plus 3. So if I add the left side to the left side, right side to the right side, for linear congruence, we are allowed to add left side to the left side, right side to the right side. So if I do that, I have A squared plus B squared congruent to 2 plus 3. Since A squared plus B squared congruent to 2 plus 3, that means 3 doesn't divide A squared plus B squared. If A squared plus B squared divided by 3 has a remainder 2, that means 3 doesn't divide A squared plus B squared. And that's the proof. Number 8, part C. let A and B be sets. Show that the set A minus B complement intersection A minus B is empty set. So to show a set is empty is not easy. Let's try to prove by contradiction. Assume it's not empty. Assume A minus B complement intersection A minus B is not empty. We try to find a contradiction. Assume it's not empty, then if a set is not empty, that means there's X belong to the set. If a set is not empty, that means there's an element belong to the set. Then, since X belong to the set, I can say that X belong to A minus B complement and X belong to A minus B. Since X belong to A minus B complement, then I can say X belong to A and X doesn't belong to B complement. And since X doesn't belong to B complement, then I can say X belong to B. Since X doesn't belong to B complement, X belong to B. Second case, since X belong to A minus B, since X belong to A minus B, then I can tell X belong to A and X doesn't belong to B. That's a contradiction. We have X belong to B and we have X doesn't belong to B. That's a contradiction. Since X belong to B and X doesn't belong to B, this event can occur at the same time. It's a contradiction. If we find a contradiction, that means our assumption must be wrong. So, if our assumption was wrong, that means A minus B complement intersection A minus B, it must be empty set. Number 8, part D. Let A, B, C be sets. Show that if A is a subset of B, then A minus C is a subset of B minus C. So let's prove it. To prove A minus C is a subset of B minus C, we need to prove every element in the set A minus C belong to the set B minus C. So let X belong to the set A minus C. We need to prove this X belong to the set B minus C. We want to show every element in the set A minus C belong to the set B minus C. So let X belong to the set A minus C. Then we know that X belong to A and X doesn't belong to C. Since X belong to A and A is a subset of B. Since X belongs to A and A is a subset of B, then we know X must belong to B. Then X belongs to B. Since X belongs to B and X doesn't belong to C, then X belongs to B minus C. Let's go. So since every element belongs to A minus C belongs to the set B minus C, then we can say that A minus C is a subset of B minus C. Number 8, part E. Let A and B be sets. Show that power set of A is a subset of power set of B if and only if A is a subset of B. So when you see the statement if and only if, you need to prove both directions. You need to assume left, prove from the right, then assume the right and prove from the left. Let's prove it. Let's first of all assume the left, prove from the right. So assume power set of A is a subset of power set of B. We want to prove A is a subset of B. To prove A is a subset of B, you need to prove every element in A belongs to B. So let X belong to A. Our goal is to prove that X belongs to B. We want to prove every element in A belongs to B. So let X belong to A. Then the set of X is a subset of A. If X belongs to A, the set of X is a subset of A. Then so the subset of X is an element in a power set. Power set contains all subsets of A. Since this is a subset of A, this set belongs to the power set. Since the set of X is an element of power set of A, and power set of A is a subset of power set of B, then the set of X is an element in the power set of B. Then the set of X is an element in the power set of B. Since power set of B contains all subsets of B, then I can say the set of X is a subset of B. Since power set of B contains all subsets of B, every element in the set is a subset of B, then I can say the set of X is a subset of B. So X belongs to B. Since this is a subset of B, then every element in the set belongs to B. Let's go. Since this is a subset of B, then every element in the set belongs to B. So X belongs to B. Since every element in A belongs to B, we can say A is a subset of B. That's one direction. Assume the left, prove from the right. Next, we need to assume the right and prove from the left. Next, assume A is a subset of B. We try to prove power set of A is a subset of power set of B. Let A be a subset of B. We try to prove power set of A is a subset of power set of B. That means we try to show every element in power set of A also belong to power set of B. And power set of A contains all subsets of A. Each element is a subset of A. So let S be an element in power set of A. Every element in power set of A is a subset of A. So I use capital letter stand for subsets of A. Let S belong to power set of A. We try to prove this S also belong to power set of B. That's our goal here. Let S belong to power set of A. Then every element, power set of A contains all subsets of A. That means every element in power set of A must be a subset of A. Then S is a subset of A. Since S is a subset of A and A is a subset of B, that's our assumption. A is a subset of B. Since S is a subset of A is a subset of B, then S is a subset of B. So if S is a subset of B, it belongs to the power set of B. So S belongs to the power set of B. So here we show that that's our goal here. So here we show that every element in power set of A belongs to power set of B. So power set of A is a subset of power set of B. Number 8, part F. Let F from A to B be a function, and let S and T be subsets of B. Show that the inverse image of S union T is the same as the inverse image of S union inverse image of T. If F is a function from A to B and U is a subset of B, the inverse image of a set U is the set of all x in the domain such that f of x belongs to U. So here we try to show these two sets equal to each other. To show two sets equal to each other, we must show they are subsets of each other. To show two sets equal, we must show that they are subsets of each other. So let's prove it. First of all, let's prove left side is a subset of right side. Then we try to prove right side is a subset of left side. So let's first of all prove left side is a subset of right side. So let X belong to the inverse image of S union T. To show left side is a subset of right side, we try to prove X belong to inverse image of S union inverse image of T. That's our goal. That's our goal. That's the setup. That's the goal. So let X belong to the inverse image of S union T. Then that means f of x belongs to the set in the parentheses. F of x belongs to S union T. Since f of x belongs to S union T, then we have two cases. Then either f of x belong to S or f of x belong to T. Then either f of s belong to S or f of x belong to T. There are two cases. Case 1. If f of x belongs to S, then x belongs to the inverse image of S. Case 2. If f of x belongs to T, then x belongs to the inverse image of T. So x either belong to the first set or it belongs to the second set. So either x belongs to the inverse image of S, or x belongs to the inverse image of T. That means x belongs to inverse image of S union inverse image of T. That's the goal here. So inverse image of S union T is a subset of inverse image of S union inverse image of T. That's first part. I show that left side is a subset of right side. Next, we want to show right side is a subset of left side. Next, let X belong to the inverse image of S union inverse image of T. We try to prove that X belong to inverse image of S union T. We try to show that right side is a subset of left side. That means we try to show every element in the set on the right side belong to the set on the left side. So that's the setup. That's the goal. Let X belong to the inverse image of S union inverse image of T. Then that means either X belong to the inverse image of S or X belong to the inverse image of T. Case 1. If X belong to the inverse image of S, then f of x belong to the set of S. Case 2. If x belongs to the inverse image of T, then f of x belongs to set T. So we have either f of x belong to S or f of s belong to T. So either f of x belong to S or f of x belong to T. That means f of x belong to S union T. Since f of x belong to S union T, then x belong to the inverse image of S union T. So that's the goal. Every element in the set on the right side belongs to the set on the left side. So f inverse of S union f inverse of T is a subset of f inverse of S union T. Since I show that left side is a subset of right side is a subset of left side, therefore they are the same. That's the proof. Number 8, part G. Let function f from a to b be 1 to 1, and let S and T be subsets of A. Show that if S and T are disjoint, then the image of S and the image of T are also disjoint. Image of a set here, let f be a function from a to b, let u be a subset of A. Image of a set is the set of all y in B in the codomain, such that y equal to f of x for some x belong to U. Here we try to show these two image of S and image of T, they are disjoint. To show two sets are disjoint, that's not easy. So we try to prove by contradiction. Proof by contradiction. assume the image of S and the image of T, they are not disjoint. If they are not disjoint, that means there is an element belong to both sets. Then if two sets are not disjoint, then there is an element belong to both sets. Then there is a Y, such that Y belong to the image of S and Y belong to the image of T. If two sets are not disjoint, then there must be some element belong to both sets. So Y belong to the image of S. Y belong to image of S. That means Y equal to f of x1 for some s1 belong to S. Y belong to S of f of t. Y belong to image of t. That means Y equal to f of x2 for some x2 belong to t. So we know S1 belong to set S, S2 belong to set T. Since F is 1 to 1 and f of S1 equal to f of S2. F is 1 to 1, that's given. F of S1 equal to f of S2, they both equal to Y. Since f is 1 to 1, f of S1 equal to f of S2. Then, by definition of 1 to 1 function, S1 equal to S2. So since they are the same, let's call it X. So let X equal to S1 equal to S2. Since they are the same, let's just call X equal to S1 equal to S2. Then X belong to S and X belong to T. So X belong to, since X belong to both sets, X belong to S intersection T. But the assumption says S and T must be disjoint. Since I find an element belong to S and T, that's a contradiction. It's a contradiction. Because an assumption says S and T must be disjoint, but we find an element belong to both sets, that means they are not disjoint. It's a contradiction. If we find a contradiction, that means our assumption must be wrong. So our assumption must be wrong. So the image of S and the image of T, they are disjoint. I'll say they must be disjoint. Number 9, part A. We try to prove or disprove the statement that for all integer a, if phi divides a squared, then phi divides a. First of all, we need to determine is this statement true or false. You can try to use some examples to verify. For example, if a squared is 0, phi divides 0, that's true. And if a squared is 0, a must be 0, phi divides 0, that's also true. And so it works when a is 0. Or if a squared is 25, phi divides 25. Now if a squared is 25, a must be phi, and phi divides phi. That looks true. Or if a squared is 100, phi divides 100. And if a squared is 100, a must be 10, then phi divides 10, that's also true. What if a squared is 400? 5 divides 400, and if a squared is 400, a must be 20, and 5 divides 20, that's also true. After trying a lot of examples, if it always looks true, then we may suggest this statement is true. We try to prove it. So, first point to tell, this is a true statement. We try to prove it. Assume 5 divides a squared. Then we try to prove 5 divides a. Since a is an integer, then by unique prime factorization theorem, I can write a as a product of prime numbers in a unique way. By unique prime factorization theorem, I can write a as a product of prime in a unique way. So a equal to p1 raised to r1, p2 raised to r2, pn raised to r sub n, where pi's are primes. Where pi are prime for I equal to 1, 2, up to n. Since a equal to this expression, then a squared can be written as p1 to the power of 2r1, p2 to the power of 2r2, pn to the power of 2rn. Since 5 divides a squared, and 5 is a prime, then phi must equal to pi. Phi must be one of these primes. Since phi divides a squared and phi is a prime, then phi must be one of these primes. For some I equal, for one of these prime numbers. Therefore, since phi is one of these prime numbers, phi also divides a. That's the proof. Number 9, part B. If A is a set of all integer x such that x congruent to 1 mod 4, B is a set of all integer x such that x congruent to 1 mod 6. Is that true? Is that true that B is a subset of A? So this is a proof or disproof problem. So for two sets, we can try to list the element out to see if that's true or not. For two sets, set A is a set of all integer x such that x congruent to 1 mod 4. So if I list the element of the set out, 1 congruent to 1 mod 4, 5 congruent to 1 mod 4, 9 congruent to 1 mod 4, 9 divided by 4, remainder is 1. 13 divided by 4, remainder is 1. 13 congruent to 1 mod 4. And the gap here is 4. 1 plus 4 is 5. 5 plus 4 is 9. 9 plus 4 is 13. On the other side, 1 minus 4 is negative 3. Negative 3 minus 4 is negative 7. And so on. That's the set of A. how is the set of B looks like? The set of B is the set of all integer x such that x congruent 1 must 6. Is that true? X congruent 1 must 6, x could be 1. 1 plus 6 is 7, 7 plus 6 is 13, 13 plus 6 is 19, and so on. On the other side, we do subtraction. 1 minus 6 is negative 5. Negative 5 minus 6 is negative 11, and so on. We can see that B is not a subset of A. B is not a subset of A. To show B is not a subset, we just need to show one element in set B that's not in A. So to show B is not a subset of A, we need to show one element in B that doesn't belong to A. So since seven congruent 1 must 6, then 7 belong to set B, but 7 congruent to 3 must 4, which means which means 7 doesn't belong to set A. Therefore, B is not a subset of A. We give one example. Show one element in B doesn't belong to A. So B is not a subset of A. Here we show that one element in B doesn't belong to A. So B is not a subset of A. Number 9, part C. Let A, B, C be sets. Prove or disprove that if the Cartesian product A cross B is a subset of A cross C, then B is a subset of C. So to prove or disprove a statement, we try to use some examples. If every example turns out the statement is true, then we try to prove it. If one of an example makes the statement false, that's a counterexample. So let's try to use an example. For example, let A be empty set. Let B be in a set of 1, 2, 3, for example. Let C be in a set of A, B, for example. Then A cross B. Empty set cross everything is empty set. A cross C. Empty set cross every set is empty set. Empty set is a subset of every set. So empty set is a subset of itself. So A cross B is a subset of A cross C. Since empty set is a subset of every set, empty set is a subset of itself. So the assumption is true. But we can clearly see that B is not a subset of C. That's a counterexample. So the statement is false. Same thing for number 9, part B. The statement is false. So to show a statement is true, we have to prove it. To show a statement is false, we give a counterexample. Number 10. In a post office, there are 8 cents, 12 cents, and 21 cents stamps. If you want to buy a total of 250 cents stamps, find all possible combinations. So let's set up the problem first. Assume you buy X 8 cent stamps. You buy Y 12 cent stamps. And you buy Z 21 cent stamps. let's set out an equation. The total number of stems must be 250 cents. The total cost of the stems must be 250 cents. So it can be, I can set out the equation as ax plus 12y plus 21z equal to 250. Ax plus 12y plus 21z equal to 250. This is a linear differential equation. We only consider non-negative integer solution. This is a linear differential equation. So first of all, let's check it has a solution. Let's check if it has a solution or not. If it has no solution, that's easy. Let's check if there is solution. We first of all find the GCD for A, 12, and 21. GCD of A and 12 is 4, and GCD of 4 and 21 is 1. 1 divides 250, so yes, there is solution. If there is solution, let's solve for two of the variables first. Let's set the equation ax plus 12y equal to w. But the GCD of a and 12 is 4. The GCD of a and 12 is 4. To guarantee the equation has a solution, we must use 4w. It must be a multiple of 4. So I need to set ax plus 12y equal to 4w. Once I set ax plus 12y equal to 4w, this equation can be rewritten as 4w plus 21z equal to 250. Next, I'll use linear congruence. I'll use congruence to solve this equation. First of all, this equation can be rewritten as 4 divides 21z minus 250. This equation is equivalent to 4 divides 21z minus 250. That means 21z congruent to 250 mod 4. 21 divided by 4, remainder is 1. So I get 1z. 250 divided by 4, remainder is 2. So z congruent to 2 mod 4. That means z equal to 2 plus 4t, where t can be any integer. Once I know z, I can substitute z and solve for w. So I have 4w plus 21z. z is 2 plus 4t equal to 250. Distribute. I get 4w plus 42 plus 84t equal to 250. Then solve an equation for w. I get 4w equal to 208 minus 84t. Divide both sides by 4. W is 52 minus 21t. Now I know w. I know z and w. Next, I can substitute w and solve an equation for x and y. Here we know z and w. I can substitute w into this equation and solve an equation for x and y. Now let's solve this equation here. This equation we have ax plus 12y equal to 4w. I can divide every term by 4. Make 2x plus 3y equal to w. Again, I use linear congruence to solve this equation. This equation is equivalent to saying 2 divides 3y minus w. So 3y congruent to, so we have 3y congruent to w mod 2. W is 52 minus 21t. 52 minus 21t mod 2. Then take 3 divided by 2, take remainder. 3 divided by 2, remainder is 1, so I get 1y. 52 divided by 2, remainder is 0. Negative 21t, 21 divided by 2 is, remainder is 1. Mod 2. So y congruent to negative t, negative 1t. I can add 2 here, make it positive. Add 2 here, negative 1 plus 2 is 1t. So y congruent to t mod 2. That means y equal to t plus 2s, where s is an integer. Since I know y, I know w, I can substitute y and w and solve for x. Two x plus 3 times y equal to w. W is 52 minus 21t. Then solve for the equation for x. I can distribute 3 first. I get 2x plus 3t plus 6s equal to 52 minus 21t. 2x equal to 52 minus 24t minus 6s. Then divide both sides by 2. S equal to 26 minus 12t minus 3s. So the solution is x equal to 26 minus 12t minus 3s, y equal to t plus 2s, z equal to 2 plus 4t, where s and t and s are integers. Next, since x, y, z, they are non-negative integers, so we have more to consider. Look at this problem here. X represents number of 8 cent stamps, y represents number of 12 cent stamps, z represents number of 21 cent stamps. That means the total value of 8 cent stamps must be greater than 0, but it must be less than the total value, 250. It must be greater than 0, but it must be less than 250. Same thing, the total value of 12 cent stamp must be between 0 and 250. And the total value of 21 cent stamps must also be between 0 and 250. First equation, divide both sides by a. $250 divided by a. I get 31.25. Since x must be whole number, so s must be between 0 and 31. Next, you divide both sides by 12. Y must be between 0 and 20.83. So since y must be whole number, so y must be between 0 and 20. Last one, you divide all 3 parts by 21. So z must be between 0 and 11.90. Then since z must be whole number, z must be whole number between 0 and 11. Next, choose a simplest equation to solve first. it looks like G is the simplest. G is the simplest. Substitute here. G is 2 plus 4t. Substitute here for G. G is 2 plus 4t. So we have 2 plus 4t is between 0 and 11. Subtract 2 from both sides. Negative 2 is between 4t and 9. And divide all three parts by 4. Divide all three parts by 4. I get negative 0.5 is less than t less than 2.25. Since t must be whole number, since t must be integer, between negative 0.5 and 2.25. 0, negative 1, 1, 2, 3. Negative 0.5 somewhere here. 2.25 somewhere here. Between negative 0.5 and 2.25, t must be either 0, 1, or 2. T must be either 0, 1, or 2. So t must be between 0 and 2. That means t is either 0, 1, or 2. So let's consider these three cases: t equal to 0, t equal to 1, and t equal to 2. When t equal to 0, I substitute 0 for each t. When t equal to 0, substitute 0 for each t. I have x equal to 26 minus 3s. Y equal to 2s. Z equal to 2. What are the possible values that s could be? What are the possible values that s could be? Let's consider x and y here. Since x must be between 0 and 31, that means 26 minus 3s must be between 0 and 31. Subtract 26 from both sides. I got negative 26 between negative 3s and less than 5. Negative 26 less than 3s less than 5. Then divide by negative 3. Divide by negative 3. Negative 26 divided by negative 26 divided by negative 3 is about 8.67. 5 divided by negative 3 is about negative 1.67. When we divide inequality by negative number, we need to switch the direction of inequality sign. So s is whole number between 8.67 and negative 1.67. So s should be between negative 1, whole number between negative 1 and a. S must be whole number between negative 1 and a. Look at y. Y must be between, so s must be between negative 1 and a. Look at y. Y must be between 0 and 20. Y must be between 0 and 20. So 2s must be between 0 and 20. Divide all three parts by 2. S must be between 0 and 10. Then, since S must satisfy both equations, both inequalities, take the common solution. Take the common solution from this equation, from that equation. S must be between 0 and a. So S must be between 0 and a. When S is 0, one of the solution is 26, 0, 2 by plugging 0 for S. When S is 1, When s is 1, I substitute 1 for s. I have 23, 2, 2. When s is 2, we have 20, 4, 2. When s is 3, I substitute 3 for s. I have 17, 6, 2. When s is 4, I have 14, 8, 2. When s is 5, I have 11, 10, 2. When s is 6, we have 8, 12, 2. When s is 7, we have 5, 14, 2. When s is 8, we have 2, 16, 2. That's the first case, t equal to 0. We have 9 solutions. When t equal to 0, we have 9 solutions. Now let's check when t equal to 1. When t equal to 1, we have x equal to 14 minus 3s, y equal to 1 plus 2s, z equal to 6. Then we try to find out the possible value for s. We try to find out the possible value for s next. Find out the possible value for s. We know x must be between 0 and 31. That means 14 minus 3s must be between 0 and 31. Subtract 14 from left side, right side. Negative 14 must be between negative 3s and positive 17. Then divide by 3. Divide by negative 3. Negative 14 divided by negative 3 is 4.67. 17 divided by 3 is negative 5.67. And when we divide inequality by negative number, we must switch direction. So s here must be between, since s must be whole number, it must be between negative 5 and positive 4. Since s must be whole number, it must be between negative 5 and positive 4. And for y must be between 0 and 20. So 1 plus 2s must be between 0 and 20. Subtract 1 from left side and right side. I get negative 1 is less than 2s, is less than 19. Then divide all 3 parts by 2. I get negative 0.5 is less or equal to s, less or equal to 9.5. Since s must be whole number, s must be between 0 and 9. Then take the common solution. Take the common solution for this two solution here. Take the common solution. S must be between 0 and 4. S must be between 0 and 4. Take the common solution. S must be between 0 and 4. So when s is 0, I have 14, 1, 6. When s is 1, we have 11, 3, 6. When s is 2, we have 8, 5, 6. When s is 3, we have 5, 7, 6. When s is 4, we have 2, 9, 6. That's the case when t equal to 1. When t equal to 2, this equation, the solution can be rewritten as x equal to, if I substitute 2 for t, s equal to 2 minus 3s. If I substitute 2 for t, y equal to 2 plus 2s, z equal to 10. Then let's find out the possible solution, possible value for s. Let's try to find out all possible value for s. We know that x must be between 0 and 31. So 2 minus 3s must be between 0 and 31. Subtract 2. I get negative 2 is less or equal to negative 3s, less or equal to 29. Then divide all three parts by negative 3. Negative 2 divided by negative 3 is positive 0.67. Negative 3s divided by negative 3 is s. 29 divided by negative 3 is negative 9.67. When we divide inequality by negative number, the direction switched. Since s must be whole number, so s must be between negative 9 and 0. Next, let's look at y. Y is 2 plus 2s, but y must be between 0 and 20. So 2 plus 2s must be between 0 and 20. Solve this inequality for s. I can subtract 2 from left side, right side. 2s is between negative 2 and 18. Then I can divide all three parts by 2. S must be between negative 1 and 9. So find a common solution here. S is between negative 9 and 0. S is between negative 1 and 9. The common solution here is that S must be between 0 and negative 1, between negative 1 and 0. S must be between negative 1 and 0. Take the common solution for these two inequalities. S must be between negative 1 and 0. Then there's only two possibilities. Either S is negative 1 or S is 0. When S is negative 1, we plug in negative 1 for S. We have x equal to 5, y equal to 0, z equal to 10. When S is 0, we have 2, 2, 10. So totally we have 9 solutions from here, 5 solutions for t equal to 1, and 2 solutions when t equal to 2. Totally there are 16 solutions. So those are the total solutions, all possible combinations. Those are all possible combinations. This combination means 26 8-cent stamp, 0 12-cent stamp, and 2 21 stamp, for example. And this solution means 23 8-cent stamp, 2 12-cent stamp, and 2 21-cent stamps, and so on. We have totally 16 solutions.